again here, one more time. We're going to continue our series on the electronics in your handy dandy electric guitar. Guess what this is? You're right, it's another tube. This is good enough if you want to make a spit wad shooter to shoot around the corners. Actually, it's a hookup tube that goes under your sink to hook up the water supply to the sink. But it does make a good spit wad shooter, should you be so inclined. Not that this, no, I ain't going there. I have shot spit wads. Okay, last week we talked about AC, or alternating current. Okay, we went over some basic alternating current terms and in terminology. We talked about the frequency, how many wiggles per second the voltage made. We talked about period, how long each wiggle took. Ooh, that looks kind of funky on the camera. Okay, we talked about amplitude, how big each wave is. Okay, this week we're going to talk a little bit more about AC. We're going to talk about Fourier Analysis. Big scary term, Fourier Analysis. That's the name of an old French mathematician, lived back at the end of the 18th and early 19th centuries. In other words, from late 1700s to early 1800s. He actually worked for Napoleon, Emperor Napoleon. He was working on heat transfer. Now, I don't know how he got from heat transfer to wave analysis or anything like that, but he's a pretty sharp dude. Okay. Fourier said, he came up with this theory, or this theorem, that any arbitrary waveform, as long as it's continuous in time, that means it doesn't start and stop, it continues on and on and on forever. Okay, and it had to meet several other mathematical restrictions, which actually work out pretty well for electrical circuits, can be broken down and expressed as a series of nothing but sine waves. It's a sum of a bunch of sine waves with different amplitudes, and different phases and all kinds of different other different things. Huh? You mean you can express just any old weird-looking wave or waveform as a bunch of sine waves? Just start adding them up. Well, yeah, you can, but the waves have to be carefully selected. Each one has to have the proper frequency, the proper amplitude, the proper phase relationship to the others. Some of them are sine waves, some of them are cosine waves, but it works. I know. The first time I heard it, I said something along the lines of, "That there's a bunch of bovine feces." Okay, that's a bunch of just purely old bovine feces. You can't express just any old waveform as just a bunch of sine waves. What about a straight line, for instance, or DC? Well, it turns out, yeah, you can express DC or a straight line as a sine wave. You just say, okay, it has an amplitude of 1 or 2 or 3 volts, whatever, and a frequency of 0. Well, okay, I'll take that. There's other ways to get to DC from it, but anyway, it's pretty cool. I put together a little demonstration here on the computer to where I'm actually going to build a waveform from a bunch of sine waves, and we'll step through it and we'll see how it works, and we'll go through it. Hopefully when we get done, I will have convinced you, oh yeah, and maybe even said, and maybe even inspired you to where you say, hey, that's kind of cool, and you can kind of play with some of this yourself. There's all kinds of tables available on the internet where you can look up what amplitudes and frequencies you have to add together to get a particular waveform. Hundreds and hundreds and hundreds of tables and hundreds and hundreds and hundreds of waveforms. I just did 2 because I don't have forever to demonstrate all the various possibilities. So let me take a couple minutes here to turn this around and get all set up for that, and then I'll show you. Okay, here we go. Yeah, I'm recording. Okay, here we go. I have written a simple program here that plots a sine wave. You can see it. It starts here at 0, goes up through a peak, down through 0, down through a negative peak, and back to 0. I've plotted 2 two waves here, or two complete cycles. Wave has this amplitude, okay, this period, okay, the distance between those two fingers is the period, and some arbitrary frequency. I actually didn't plot it as a function of time. It's a function of the position along the screen. But anyway, that doesn't matter. We got two complete waveforms. Now I'm going to add the third harmonic. I'm going to put the third harmonic up here. Okay, there's the third harmonic of our original sine wave. Here's our original sine wave. You see there's 1, 2 bumps. Here's our third harmonic, so it should be 3 times that frequency. So I should have 6 bumps. 1, 2, 3, 4, 5, 6. Okay, 6 bumps. Yeah. Now what I'm going to do is I'm going to add those two together. And that by add, I mean I'm going to take this distance right here, and I'm going to add it to this distance. This distance for the red, or the third harmonic, plus this distance for the green, or the fundamental, and I'm going to plot that on here. Now you'll see right here they're both above 0, so they're going to add up. It's going to make the sum is going to be a little steeper. Right here, the red one is below 0. It's negative. So it's actually going to subtract from this. Okay? So let's add those two together. Boom. There they are added together. And here's our sum. Now you'll note where this one is negative, it actually pushed that original waveform down. And remember, right in here, they were pretty much on top of each other. Well, now the sum is a little steeper. It comes up a little higher. So here's our fundamental plus our third harmonic. Let's take third harmonic off of there. Okay. Now that's just the fundamental wave plus the third harmonic. Let's put the fifth harmonic on there. Boom. There it is. Fifth harmonic. 2 waves. I should have 10 humps across there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is the fifth harmonic. Let's add those together. Look, they're both positive again here. You see this? Here's a negative. It's negative in here, so it's going to push this part of the waveform down. But look here where this one is at a low point. Now that it's a high point, so it's going to push this up. It's going to pull this down. It's going to push this up. So let's add them together and see what we get. Boom. Okay. Pretty cool, huh? There's our fundamental plus our third harmonic plus our fifth harmonic. Let's keep going. Seventh harmonic. 14 bumps across there. You can pause the playback and count them if you want, but hey, we can all count to 14. Add those together. Boom. Now we get this. That waveform's starting to look kind of odd, you know. It don't look like a sine wave at all anymore, does it? Looking odd. Ninth harmonic. There it is. Add it. Oh, this is starting almost. Yeah, it don't look at all like a sine wave anymore. It's starting to look like something really crazy. Let's add some more. Let's add another one. Let's add another one. Let's just add a whole bunch of them here. I'm not even counting anymore. My program is not exactly lightning fast. It has to do a lot of calculating, a lot of adding, but there's a whole lot of points across here that it has to add one at a time. So it's not exactly lightning fast. But it does get there. And of course, I have no idea how many of these things I've added now. But look, I've taken a bunch of sine waves, nothing but a bunch of sine waves, and I've added them together, and I've got a pretty good approximation of a square wave. That's right, I'm getting straight lines from adding up nothing but sine waves. Now, let's scooch the camera back out. Let's pause again. Whoop, excuse me, I got my wiener dog here. Come here, wiener dog. Hey, say hi to everybody. This is Tinkerbell. Yeah, she's named after the Tinkerbell down there in Florida. Okay, so what does all of this mean to a guitar player, a guitarist? Okay, It means just exactly what it said. Your output waveform from your guitar is nothing more than a series of sine waves of varying amplitudes and frequencies. If you want to change the sound of your guitar, all you have to do is change which ones of those sine waves get through to your amplifier to shake the speaker. Okay, you can maybe make the higher frequencies a little louder in comparison to the bass frequencies, or maybe make the bass frequencies louder compared to the high frequencies, the treble frequencies. So you can pretty much hear that, when you listen to different models and types of guitars. There's an easy way to show that, to plot that, to show the amplitudes of the different frequencies that come out of your guitar. Show how big the bass, how large the amplitudes of your bass frequencies are versus how large the amplitudes of your treble frequencies are. That is called a plot of the spectrum, or the spectrum of the guitar. I just happen to have a program that I put on my iPad, which is pretty useful. It does a good job of showing you the spectrum, and it's cheap. It was like $3.25. If you want to get it, and you have an iPad, then I suggest you do so. Let me take my cool humidifier out of here. Homemade. Hey, I just thought, what's that made out of? It's a tube. Who'd have thought? I didn't even think of that. But anyway, that's the homemade humidifier. If you don't know about keeping your acoustic guitar humidified in the in the winter months, I suggest you get on Randy Schardiger's website, on his YouTube channel, and check it out. It's very important. And it's just a simple spectrum analyzer. Let me zero it here. Here it is zeroed, and you can see my voice on there as I talk and watch it change, and see that I've got some 116 hertz in here and some 323 hertz in here. Let me zero it again. That is the spectrum, the output spectrum of my guitar plus my voice. And you can see, okay, there's some 111 hertz, and this is actually, let's zero it again. There we go. So you can see you can see me talking over it and see the spectrum change as I talk. But you can see acoustic guitar, you see a lot of bass in it, and you can hear a lot of bass in it. And let me turn that around here where I can use my right hand. And later on we'll be putting one out of recording time there, but we'll continue next week, and we'll talk a little bit more about spectrum and spectrum analyzers, and then we'll go on and start talking about circuit simulation and circuit simulators. So until then, keep on picking.